Good afternoon, everybody. I hope you are enjoying our snow day, or more appropriately called an ice day, I suppose. If you just heard that, that was Pistachio flying around. She says hi. Um, so the purpose of this video is to do what I would normally do in class after we do the Gear Lab, explain why it's set up the way it is and why I gave you the Gear Lab before I taught you about it. The reason is it's to get you familiar with it and start trying to make your own conclusions on what happens with gears. Because sometimes if you think through it, you can teach yourself at least somewhat better than I can. So this was supposed to guide you through some of the different things that you'll see with gears. And so I want to go through and explain what each question was trying to show you. So if we start with question 1, we're going to start by removing all the other gears, so that we have the same situation as you should have for question number 1. And we can see here we have a 8-tooth gear, which is a fairly small gear, and we can look at the dot and see how fast it's moving. To me, it doesn't look like it's moving very fast. So we're going to try and up the number of teeth. So let's go all the way up to 400. Now it's not on the screen, so we're going to zoom out. And just right off the bat, these teeth look like they're moving a lot faster. Now, we have not changed the RPM, so the revolutions per minute, so how many times this goes around every minute, but we have made the gear a lot bigger. So this dot that we just saw going by pretty darn fast is moving around the circumference of the gear 6 times every minute. Okay, that's what RPM means. So it goes around 6 times every minute. So there's 6 revolutions per minute. Now, this gear is a lot bigger than our first gear, right? This one has 400 teeth that are the same size as each of those 8 teeth. So this one has to have a much larger circumference. That means that despite the fact that our RPM has not changed, the edge of this gear is moving significantly faster. And we can see that by how fast the dot is moving. Now, what this question and then the next question, number 2, are supposed to try and get you to see is that there's a difference between our idea of speed, what we normally see as speed or linear speed, and this idea of revolutions per minute. Okay? So, like I said before, revolutions per minute is how many turns that gear is going to make each minute. That doesn't tell us anything at all about how fast the edge is moving out here. Because we know that this gear probably has a circumference that's significantly larger, and that means that every time that dot goes around, it has to physically move a bigger distance, which means that it has to move faster. So this linear speed is physically how fast the dot on the edge is moving. Your RPM tells you how fast or how many times it goes around every minute. Now, the reason why we use RPMs for wheels and gears and things like that is it is much, much easier to measure. Because if we have this gear, this big gear connected to a shaft, the edge of this gear is going to be moving way faster than the little itty bitty tiny shaft that is connected to it in the center. But if we're just looking at how many times it turns every minute, they're both going to be the same. So for our calculations and for measuring things, RPM is going to be a much easier measure to use. Okay? So for your first question, you should have seen that the dot was going faster on the big gear. And then for the second one, despite the fact that it's going faster, it should still take the same amount of time to make each of those revolutions. If you have more questions about the difference between linear speed and this rotational speed, as it's commonly called, or rotations per minute, we will hopefully be back in school sooner than later, unless it continues to ice and snow every day. And then we can talk about it a little bit more in person, because it's a little easier to explain if I have you guys asking me questions directly as I'm explaining it. So That is the idea between 1 and 2. It's to try and get you to see this sort of difference between rotational speed and the speed that we're more used to, which is linear. Number 3, yes, I know it's just a chart, but the whole idea behind the chart was to try and kind of allow you to test your own values and see how that changed the way the gears react. So let's make our gear a slightly more reasonable size. Let's maybe do 10 teeth on this gear, and then we'll add another one, and that's a 13 tooth gear. So that's good for now. Now, part of the reason why I told you to keep your RPM for gear 1 the same is because this is the gear that is driven by a motor. Okay, so this is setting your speed of your first gear. Like I told you in the video or in class, we should pretend like there's a shaft that kind of runs back down below this grid and is connected to a motor. Unless I change this speed, which is the speed of the motor, changing the size of this gear is not going to change how fast the motor is turning it. So if I made it 100 teeth, the RPM still remains the same. Now, obviously the RPM on the second one has changed, but the RPM of the first one still remains the same, because no matter how big or small this gear is, it doesn't affect how fast it's being driven by the motor. So part of the reason, let me go back to what I originally started with. Part of the reason why I had you leave the RPM for gear 1 the same is because when you are doing a scientific test, you really only want to test one changed thing at a time. And so here we have 4 columns on our chart. We have the number of teeth on gear 1, the RPM for gear 1, and then the teeth on gear 2 and the RPM for gear 2. Now, for a good science experiment, you should really only change one thing for each trial. Now, each line on this chart kind of acts like a trial. So maybe we start with 100 teeth on gear 1, so we can see that right there, and an RPM of gear 6, because we haven't changed the speed of the motor. And then we have our 13 tooth gear here, and we see that we get an RPM of 46.15. Now maybe next time, instead of having 13 teeth, we have 15 teeth. And we can see that by changing the number of teeth on gear 2, our RPM went down. So as we got more teeth, so this gear got bigger, our RPM got a little bit smaller, okay? Now, if we make this gear, our driving gear, smaller, so let's make it smaller than gear 2. So now we can see that this gear is smaller, and so every time it turns around, it only pushes 10 teeth of gear 2 past it. So here we have an RPM of 6, here we have an RPM of 4, okay? So the purpose of this chart was to allow you to kind of go through and test out different combinations so that you can see for yourself that if this gear, the driving gear, is smaller than the gear it's driving, so gear 1 is smaller than gear 2 is going to have a smaller RPM than gear 1, whereas if gear 1 is bigger, let's make it 20, this gear is now larger, so our gear that's driving it is larger. This gear is smaller, so 1's bigger than 2. And we can see that our RPM has gone up for gear 2. So if we have a smaller gear driving a bigger gear, the bigger gear is going to go slower. If we have a bigger gear driving the smaller gear is going to go faster. Another way to think about it is kind of what I mentioned at the beginning. Every time this first gear turns, it's got 20 teeth, so it's going to push 20 teeth past it. This gear, our second gear, only has 15 teeth, so this gear has to turn more than once for every time this one turns once. Hopefully that makes sense. So that's kind of what you were supposed to see as you were using the chart. It was supposed to kind of help guide you through how that all works. Now, the next 2 questions I gave you specific values to put for your number of teeth. So gear 1, I wanted you to have 40 teeth. Let's put that in. And gear 2, I wanted you to have 20 teeth. Now, notice here, gear 1 has 40 teeth and an RPM of 6, and gear 2 has 20 teeth and an RPM of 12. Okay? These two examples are specifically supposed to help lead you to get to a more detailed relationship between these two gears. So notice I have 40 teeth and 20 teeth, okay? 20 is half of 40, okay? We have 6 RPM on this one and 12 RPM on this one. That's twice as many RPMs, okay? So we have half the number of teeth and twice the RPMs, okay? So that's something that you should note. Now, we are going to go to number 5 now. So here on gear 1, we should have 60 teeth. And gear 2 is still going to have 20. So 60 teeth, 20 teeth. So that's a third of the teeth. And this gear has 6 RPM. And this gear has 18, which is 3 times the RPM of gear 1. So you should start to see some sort of a pattern going on here. That ratio between our number of teeth is the same number as the ratio between our RPMs, okay? And this is what should help lead you into being able to answer number 6. Now, if you were in class, I told you that you could possibly find a mathematical relationship or an equation for this. I think I mentioned it on the video if you carefully watched the video if you weren't in class. So if you found a math equation to answer number 6, that is a perfect answer. If you did not, that is perfectly fine. I know you guys aren't used to coming up with math equations. So let's talk about how we could possibly get to the equation for this. Okay, so first, we know this is a simple machine. So we're going to have some sort of an equation that's going to be similar to the ones that we've used for both levers and inclined planes. So we're going to have some sort of an idea of force times distance equals force times distance. Now, hopefully, you've kind of gotten this idea, or when I say it, you can understand it, that the number of teeth on the gear is going to pertain to the size of the gear. So the more teeth around it, the bigger distance the outside turns, okay? So for gears, our measure of distance is going to be replaced by our number of teeth because we're using the number of teeth kind of like a different unit of distance, okay? Our RPM, it's a little bit harder to see how this is a unit of force, but it is very much directly related to how much force is applied to the gear. Because you have to apply a certain amount of force to get it to turn that many times per minute. Okay? So what we end up with is instead of force times distance equals force times distance, we get RPM, which replaces our force, times the number of teeth, which equals our RPM times the number of teeth. Okay, I think this will work. I have it typed out for you guys so you can see it. Oh no, it's not going to, it's not going to go over. Sorry about that. I've not used Screencastify that much to record the screens. Anyways, it did not show up, but hopefully you can kind of see that it's RPM 1 times RPM 2, or sorry, RPM 1 times teeth on gear 1 equals the RPM on gear 2 times the teeth on gear 2. Okay? So that is actually going to be our equation. And what we can see here is actually if we solve this equation so that all of our teeth are on one side and all of our RPMs are on the other. So if we did that, we'd end up with RPM 1 over RPM 2. Okay, so we've got RPM 1, RPM 2 equals teeth on gear 2 divided by teeth on gear 1. So we actually have what you are used to in your math classes as being a standard ratio. And so we can see that if we have 3 times the number of teeth on gear 1, we should also have 3 times the RPM on gear 2. So, like I said, if you have questions on that, you can email me. I do also want to talk about this a little bit more once we are back in person so that I can get your feedback as we talk about it. All right, so that is question number 6. Now for 7, we need to add a new gear. Okay, so with what I told you in gears or in 6, this should actually be a little bit easier. Okay, so let's see. First things first, if you hadn't found the equation, you can look at this and say, okay, this is too big. So if I add more teeth on, I'm going to get that lower. Okay, and like I said, I recommended that you stay with an RPM of 6. And after what we talked about, that should make a little bit more sense because 6 is, you can multiply 6 by 4 to get 24. Okay, so that makes it easier to get that 24. So if you had changed this to like 5, that would make it really, really hard, actually kind of impossible because you can't do partial teeth to get that 24. Okay, so here, if we look, we know that 6 times 4 is 24. And if we look at our number of teeth that gave us that final RPM of 24, we see that we have 15 and 60. Okay, now notice that I'm ignoring the gear in the middle. I want you to watch what happens when I change the number of teeth on the gear in the middle. Okay, as I'm changing it, watch this RPM. I'm guessing that's probably not what you expected to happen. Okay, so we will go through this in class. I'll actually write it all out on the board, but this middle gear can be whatever size you want it to be. We can take it up to 400, and it will still end up being an RPM of 24 on the last one. We can make it 4, which is as small as this will go, and that will still remain 24. Okay? And the reason for this is if we actually wrote the equation out, we would go from this gear to now our second gear, and that would give us a set RPM. And then we would do the same thing to go from this gear to this gear, so that's from the second to third. And when we actually look at that math, all of the stuff for the second gear shows up in both equations and ends up canceling out completely. So all we're left with is the ratio from that first gear to whatever gear we have in question. And this will actually make your assignments a lot easier once we start doing problems with gears with the actual equation, because you can ignore all the gears in the middle and just look at the 2 gears that we are actually, or the question is actually asking about. So that's almost all of the questions that I got and some extra information that I threw in. The other one comes from, where does this idea that they talked about in the video that we watched on Wheels and Axles, where does this idea of you get a trade-off of force and distance or force and speed come from? Because here we've really only talked about our RPMs and our number of teeth. So The one fallback of this program is there is no aspect of force, okay? This program is actually made to design gears so that you can 3D print them or use, say, like a CNC machine to cut them out yourself. Um, because of that, they assume that you're going to be doing the force calculations beforehand. So let's go back and kind of talk about a bike for a second. We all know that if you try and go up a hill on a bike and you change your gear, it's going to make it easier. So if you turn your gear down, it's going to be easier to go up that hill. Okay? Now, you will go slower. And so this is a very clear indication that the faster we go, the more force we have to apply. Okay? And this is actually where gears or wheels and axles or anything like that start behaving very, very similarly to a lever. Okay? So you can kind of pretend like this is a lever and it's going to have a arm that goes from the center out to the edge, and we're just kind of turning it around. Okay? So if we have a long lever and you're holding on to the middle, so think about like you have a really long piece of wood. Okay? It's going to be pretty hard to move that end of the wood really fast. You have to apply a lot of force, and that's what's going on if you have a bigger gear. Okay? It's hard to take that force in the center and move the end really fast. Hopefully that kind of makes sense. Now, if we have a little gear, so if we look at this little 4-tooth gear here, that would be like you have maybe like a short ruler instead of a really long 2x4, okay? A ruler is going to be much easier to move quickly than that really long 2x4. But the difference is the end of that 2x4 moves a lot farther. Okay, so when we translate that to a wheel, every time this wheel goes around, if it were on the ground, you would move a big distance. So even though it's hard to turn that wheel that fast, you're getting a big distance payout for every time you turn that wheel. Now, if we look at this one, that wheel is going to be really easy to turn, but you get a really small amount of distance out for every time you turn it. Okay? So this is where we see that trade-off of force and distance. And most of the time, the analogy of it being like a lever is one of the easiest ways for people to understand. All right, this video is getting kind of long, so I do want to stop there. If you guys have any other questions, please email me, and I will try and make another video answering those questions, or if we're back in school tomorrow, I will answer them in class. Have a great afternoon. Hopefully you go play out in the ice and snow, and stay safe.